Today in this presentation, I'm going to talk about the use of nanotechnology in enhancing the impact absorption and energy dissipation ability, especially applied in the new body armor. First, I'm going to talk about the background information on the current body armor and what's need to be improved. In the recent warfares, we're using increasingly powerful explosive devices, which can produce the blast shock waves. The energy carried in these waves propagates rapidly and dissipates quickly, which makes, however, they weigh as much as like 40 pounds, which is very burdensome and inconvenient in the battlefield when the soldiers need to move around very quickly. Furthermore, even if it successfully stops the bullet, as it's designed to be, it can only expand the impact over a larger surface on the target without even absorbing or attenuating the impact, which makes the soldier usually get severely injured, including broken bones and internal bleeding. Thus, the advances in body armor are critical for the national defense to save the soldiers' lives. The Institute for Certain Nanotechnology, ISN, is an Army-supported and university-affiliated US research center. It aims to use the power of nanotechnology to advance the armor protection and to enhance the soldiers' survivability through collaborating with the Army and industry partners. And I'm going to mainly talk about three core technology that is crucial to improve the energy dissipation, impact absorption capability of the body armor. The first one is the superelastic granular materials. Oligocrystalline is one of these materials, and it's a new class of shape memory materials which can dissipate mechanical energy through interparticle friction and intraparticle martensitic phase transformation. A unique feature of the oligocrystalline is that its total surface area is greater than the total grain boundary areas. As you can see from the graph, the contact area of these two particles is far less than the surface area, which gives them more free and confined surfaces rather than the rigid boundary areas. And the shape memory materials are a class of smart materials that is able to undergo a large reversible deformation under loading like stress and thermal cycles. During these cycles, they convert heat into mechanical strain and the other way around, which means they are deformed when absorbing the shock waves and are capable of restoring their original shape when heating up. This ability is also referred as superelasticity. These changes are achieved through diffusionless transformation, which can be interpreted as a reversible martensitic transformation between a crystallographically more ordered parent phase, the austenite, to a less ordered product phase, the martensite, as it's illustrated in the graph. In the graph A, it's the original austenite, which is pretty like standing up straight, and then when you apply a load on these particles, it deforms into the martensite and just become bent. And after the heating up, it restores its original shape of a like standing straight up austenite face. In terms of, they are capable of equip the body armor with the ability to sense their environment and modify their behavior in extreme circumstances, because they can form composite structures with the embedded sensors and actuators, which can look for cracks and corrosion and remind the protected soldiers of these defects, and even counteract the strain induced by degradation of the body armor, protecting the soldiers from being further injured in subsequent combats. The second technology is the liquid armor, because the movement and coordination of the current solid armor always transfer the energy of the blast shock to the protected soldiers, which results in severe injuries called the non-penetrating injury. Therefore, we are trying to apply liquid property to mitigate impact and prevent the shockwave from penetrating to the victim. The first technology in the liquid body armor is the hydraulic energy redirection system, which includes the liquid-filled plastic tubings, which is able to transfer the kinetic energy of blast shock waves into hydraulic energy to redirect and redistribute the energy to the lower end of the liquid-filled piping system, as you can tell from the graph. The design is particularly used for the energy redistribution process. The liquid-filled design can offer protection against the blast shock waves and the overpressure caused by the body armor, and protect the human body of the soldiers. The second liquid armor technology is the shear thickening fluid integrated armor, also called the SCF integrated armor. Shear thickening fluid are special materials with nanoparticles that exhibit the properties of both solids and liquids. It's made by mixing the nanoparticles and a low molecular weight polymer to form a colloidal suspension, which is basically a mixture of solid and liquid particles. And normally, it exists in a flexible and fluid-like state under normal conditions, but it hardens rapidly under high-velocity impact, which in the battlefield, when you get shockwave or bullet, which can offer appropriate protection. There's no doubt that the revolution of next-generation body armor lies in the core potential of nano-enhanced materials, which can give rise to plenty of the ideal properties, including increasing flexibility, more strength, comfort, and decreasing weight added upon the soldiers. The outstanding impact absorption and energy dissipation capabilities mentioned in this presentation, associated with particular nanoparticles, are gradually transforming our imagination to reality